Alright, section 6.4 here. This one's dealing with what's called the chi-squared distribution chart. We'll be using that to help us with these problems. That one is in the back of your book. If you have the fold out pages, it'll be one of those. It's labeled chi-squared distribution. Or if you're looking in the appendix, it'd be A19 is the page that chi-squared distribution is at. So just after the other ones that you have related to the normal distribution and t-distribution, it's right after those. So for this first one here, we have to find the critical values for the chi-squared R and L for the 90% confidence interval if the sample size is 20. So first of all, for picturing this, what we'd have here is we can draw it out similar to our normal distribution table. It looks similar in terms of the curve, just not symmetric. Because you'll notice in the chi-squared distribution chart that all the values are positive, so we don't have any negatives for the values like we had in our normal distribution charts before. So here, if we're talking about 90%, kind of like that one that we had to find for the 92% back in section 2, we'd have 90% is in this section. So if 90% is there, that means there's 5% on either side, similar to what we had before for our normal distribution chart. And then here we're dealing with a sample size of 20. So kind of like I talked about a couple sections ago, we have what's called our degrees of freedom. DF. DF stands for degrees of freedom, which is how it's labeled in the chart. Looks like for the chi-squared distribution chart. Label says degrees of freedom. It writes it out in words. And to find that, once again, you do your sample size minus 1. So in this case, our degrees of freedom is 20 minus 1, which gives us 19 for our degrees of freedom. And then we also have to use our values that we had here. We have the 0.05 along with the degrees of freedom of 19 will give us one of the values. So here, if we look up at the top where it has that alpha symbol along the top, we have a bunch of different values there. For one of these, we're going to have to look at the 0.05 and then go down from the 0.05 column down until we get to degrees of freedom of 19. And then we want to look to see where those two intersect at there. So if we look at that, in this case we get 30.144, and that's actually going to be this upper value here, this 30.144. So another difference here that you'll notice if you look at the top of that chi-square distribution table is that if we're dealing with a right tail, so if we're dealing with the right-hand side here, that's actually the values that are given in the table there, that 0.05. So this is what's called your chi-squared R value. You'll see it written in your book as chi-squared. And then the little subscript of R means it's the right-hand value. If you're not sure which one has to be which, you can always write the bigger one on the right side once you found both of them. So to find the other value, so one of them, like I said, was this 0.05. The other value that you look up for the alpha value is going to be 1 minus that 0.05. Or in other words, in this case, it'd be 0.95. So the other alpha value, the value along the top that we're looking for, is 0.95 this time. And then we go down to degrees of freedom of 19 again. And if we do that in this case, we get 10.117. So just like whenever we're dealing with confidence intervals, number lines, all that, the smaller number goes on the left side, and that's why that's called the chi-squared L for the left side. And then chi-squared R is on the right side, the bigger number. So that's the basic idea in terms of finding those critical values for a chi-squared distribution using the degrees of freedom and using the values that you have whenever you split that 90% confidence interval along both sides there. So you can think of it as 5% on the right side. Actually, there's 95% below that, which is why we looked up 0.95 for the other value. Then if we go to a specific case here, for example 2 here, we have that you randomly select and weigh. In this case, I'm going to need to change this value. I didn't notice that first. We're going to change that to a 41. So if you look in your chi-square distribution table, we don't have a degree of freedom of 39 anywhere in that table that we can use. We only have degrees of freedom of 40. So we'll change that value to 41. So that way our degrees of freedom, whenever we do our n minus 1, gives us 40 here. So 41 minus 1 gives us 40. So we'll change that there. So edit that in your notes. And then we have a sample variance of 1.02 ounces. Assuming the weights are normally distributed, construct a 95% confidence interval for the population variance and standard deviations. So first of all here, we're going to have to find our chi-squared L and chi-squared R values again here, because those are used in the formulas. In this case, we had 95% confidence interval, which means 95% or 0.95 is in the middle part there, which leaves 2.5% on either end, or 2.5% as a decimal is 0.025 would be on either end. So then we have our degrees of freedom here of 40 in this case from doing our n, the 41 minus 1. And then to look up this value, kind of like the first example, we can go ahead and do the right end first. We can do that 0.025 along the top that we're looking for. And then go down to our degrees of freedom of 40. And see where those two intersect there to get that value. So in that case, we get 59.342. And then like the last one, we're going to have to do 1 minus that 0.025 to get what the other value is that we have to look up in the table. So the other one is not the 0.95, it's 1 minus that 0.025. So in this case here, if we do that, we get 0.975 is the other one that we have to look up. That'll give us the left-hand value. So remember, this is chi-squared R here. Get the chi-squared L. We now have to look at the 0.975 column, go down to degrees of freedom of 40, see where those intersect. So in that case, we get 24.433. Just like before, use all the digits that it gives you in the table. No need to round those. And that would be our chi-squared L. So that's in terms of the critical values first of all. And then we have to plug them into the formula that we have related to this stuff. So our formula, whenever we're dealing with the sample or the population variance one, so first of all for that one, write out our general formula here. We have n minus 1 times our sigma, or actually sigma squared, or a lot of times instead of sigma squared, put off to the side here, you might have s squared instead from the sample variance. So let me actually write that in instead, because that's what you'll have most of the time, is just the sample values. Write it in there as s squared. And then divide that by, on the left side, you actually divide by chi-squared R, because if you divide by a bigger number, it makes the overall fraction smaller. And then that's going to be less than your sigma squared, the population variance that you're looking for. Just less than your n minus 1 times s squared over chi-squared L. And this formula here will be given to you if you need it on the quiz or the test. That'll be one of them that I'll actually give to you if you need it. You just need to know how to use it here. So here then, in this case, for our variance, we plug in our n minus 1, we already calculated that, that's 40, times the sample variance. So remember the s squared is the variance. If it was just s, so in this problem, if it gave you standard deviation instead of variance, then you'd have to do the standard deviation squared. So you do want to be careful whenever you're reading that also of whether it gives you a variance or a standard deviation. That'll depend on whether you have to square this number or not. And then divide by your chi-squared r. And then we have our population variance there that we're looking at. And then 40 times that 1.02 divided by chi-squared L, which is that 24.433. And then you want to calculate those out. In this case, we get about 0.6875. Go out at least 2 decimal places for these. The more digits you go out, the more accurate it is. And then 1.6699 here. And then just like before, once you have that variance, the quick way to get the standard deviation is to then square root these answers that you just got. So rather than having to go through and recalculate it all and then do the square root like it has in the book for you to do, what you can do instead now is you can then just go through and square root that 0.6875 and square root that 1.669 there to get those two values. So if we square root the one on the left side there, we get 0.8292. And then for the other value here, if you square root that, we get 1.2922. That is once again from doing the square root. Remember your square root symbol? In case you get some of those mixed up there, that's your square root symbol. So you square root both of those to then get your standard deviation value. And then in general, some of these will also ask you to then interpret your confidence intervals here. So remember, in terms of interpreting, you're just saying, for instance, in this case for the variance, you can say that you're 95% confident, abbreviate it here since I'm running low on space, confident that the population, we'll abbreviate population variance, is between those two values that you got here. So between the 0.6875 and the 1.6699. And then you could do the same sort of thing for the population standard deviation, which is the second one, that you're 95% confident that the population standard deviation is between that 0.8292 and the 1.2922. So it doesn't have to be real tricky for those interpretations there.